Thanks again for joining to this Inria-NAFEMS session. It will be a full afternoon that we like to call the Technology Day between Inria and NAFEMS. Today it will be focused on innovation in healthcare using organ modeling and simulation. You're going to discover different topic of research, different topic regarding different softwares, and different industrial applications. All that always with an emphasis on robotics and medical devices applications. So we're going to start first with a research session. Sorry for repeating that again and again, but just for the newcomers. So we're going to start with this research session with 3 different presentations. It's going to be 15 minutes each, including questions. And after those 3 presentations, we're going to have again 15 minutes in breakout rooms so that we can take the time to discuss with each of the speakers. Okay? So we're going to start today. It's my pleasure to welcome Stéphane Cotin, a professor at Inria, working on the topic of medical simulation for a long time. He's going to talk about Bayesian inference and neural network, and to explain how those data-driven simulation can actually be used in surgery. So thank you, Stéphane, for presenting us your work today, and the floor is yours.
Thank you, Hugo. In our team, what we do essentially is to look at how we can use numerical simulation as a way to reduce risks with patients and reduce medical errors in a way. And it starts all the way from surgical training and goes from there to surgical planning, where we use here a model of the patient to basically prepare the surgery. And at the other end, we have tools that we try to deploy in the operating room to provide guidance. And it can come in the form of visual guidance, like augmented reality, to show the internal structures of the organ, all the way to control in robotics. And here are some examples of what we do, okay? And again, I took a subset of our research, but just show you that these different topics can take different shapes and forms depending on the clinical context. But the key is that in many of the applications we have and the problems we try to solve, the main problem we're dealing with is soft tissue biomechanics, okay? And since we are trying to provide guidance in a clinical context, we want to make sure that we are as accurate as possible, meaning that we need to use complex biomechanical laws, such as hyperelasticity, sometimes even visco-hyperelasticity. And of course, these models need to be parameterized for a particular patient in most of the applications, again, I described for planning and for guidance. And they also need to be as fast as possible because in pretty much everything I described, computation time is key, since we always need to be real time and have a user in the loop. And since we're dealing with partial differential equations, our, I would say, numerical method of choice is the FEM method, where we discretize the domain, which is usually a complex domain, in the finest possible way. And we've tried different strategies in terms of what type of elements to use, but we're always facing the same dilemma, which is that on one end, we need a fine discretization to be as accurate as possible when it comes to numerical errors. But on the other end, we need to be as fast as possible to meet this real-time constraint we are facing. So I will describe some of those steps and how we can use them in an actual clinical context. And I'm taking the example that I often use of augmented surgery. And in this case, what we are trying to do is to provide enhanced visualization for the clinician, like the one you see in the upper right image, by overlaying in real time the virtual organ of the patient that we obtained from the preoperative images on top of the actual image of the surgery. Okay, so that means we need to deform the preoperative model using a very fast finite element approach, and also use information from the image to make this deformation fit what we actually observe. And of course, this requires a patient-specific model if we want to be as accurate as possible. And so it really fits this definition of a digital twin, where you know, this idea of a digital twin is to use data from sensors. In our case, sensors are images most often, to extract data and parameters for this virtual digital twin, to update the model, and in turn use the model to provide added information to, in our case, the clinician. So it's basically creating a sort of a closed loop feedback where, you know, the model learns from data, and the data is in a way enhanced by the model. So this link that the twin creates between the physical and digital world is really what we're trying to do in this case. And since in our case, images are our sensors, we need to extract information from these images, and it often comes from either artificial markers that we can place on the organ, or ideally natural texture patterns or additional information like the contour, the silhouette of the organ. And the key is then to link this information coming from the image to the virtual model of the organ, and the biomechanical model. And what we used to do was to basically take this information extracted from the images and use it to drive the deformation of the model. But by doing so, so it's what's called registration in our field. But by doing so, we're basically applying virtual forces onto the organ that don't necessarily exist in the real world. And so we went from this approach to a Bayesian approach, where rather than applying those virtual forces, we're trying to learn from the errors, the discrepancy between the model and the observations, a parameterization of the model that will reduce these errors. Okay, and this is what I show in this slide, where here we're learning from an image. So it's a video of manipulation of a liver lobe in a porcine model. Okay, the little colored dots, they correspond to different features we are extracting from this image. And what you see, that there's different curves that you see changing over time, are parameters that we are estimating in real time and basically feeding back into our model. And the model is not just, you know, the liver and its parameters like the Young's modulus, but it's also the boundary conditions. So we're also understanding that the boundary conditions play a key role in this. So we're also learning the boundary conditions from observations of the surgery. And in this case, what's interesting is that through this approach, we are estimating parameters that we don't directly measure. Okay, and I think that makes it very suitable for the kind of application we're looking at. And it's quite fast, it's quite accurate, and it allows us to already bring some of these ideas into the real world by providing surgical guidance. And here, these are two relatively old images, but videos of two different surgical contexts. One in the case of minimally invasive surgery, robotized surgery. The other one is in open surgery. In both cases, we're using information coming from the images to drive, again, the deformation of the model, but also learn from these images a better parameterization. Now, this is all nice, and we've actually showed through some clinical studies that we can get accurate to about 5-6 millimeters when it comes to estimating, for instance, the location of the tumor. And it's relatively fast, but I would say it's not enough. It's not enough because or the clinicians we work with, would like the accuracy to go below 3 millimeters. And on the other end, if we also want to use these models in the control loop of a robot, we need the highest possible, I would say, refresh rate of the model, so update frequency. So to try to achieve both objectives, we, about 4 years ago, went for a different strategy where we wanted to replace the finite element method with a deep learning approach. And the reason we chose deep learning is it's a good, I would say, approach to learn complex relationships. And it's also an interesting method because when we look at a particular network architecture that we chose, that already existed actually before, but we derived it, I would say, from its initial usage, which is the UNet. We realized that when we train through a UNet architecture, we're doing something similar to model order reduction. So in the encoding path, which is basically the first part of the U, when you get to the bottom of the U, the vector of features we obtain is very similar to the reduced space we obtain with model order reduction. And then the decoding path basically expands back to the original dimension of the problem. So it allows us to have a training mechanism that can learn the complex deformation of physics-based object like the liver, but it can be pretty much anything you want. And you can see in this slide that the prediction of our network is nearly identical to the finite element solution, but it's about 300 times faster. So it's very fast, it's quite accurate, and it can really learn already a quite generalized prediction in the sense that the only thing that is fixed in these predictions is the shape and the Dirichlet boundary conditions. For the domain boundary condition, you can pretty much prescribe everything you need. So the network has been trained on a very large variety of external forces. And it's, again, very fast and quite accurate. But again, we wanted to go a step further and in particular improve both the speed and the accuracy of the prediction. And we went to a slightly different approach, first by using a different network architecture, which is a fully connected network, which I think gains a little bit in terms of computational performance. But then the main difference is that we replace the loss usually used in most of the training methods, which is the MSE, which is basically a geometric measure of error, by a measure of error which is based on the physics. Okay, so here we use the internal forces of the simulation to predict or to measure basically the error in the training process. And this leads to a significant gain in terms of training speed and predictive accuracy. But then, even if we really got very, very good results with this, a neural network, you've seen probably examples of that before, can work really, really well in 99% of the cases, and then in 1% provide completely wrong solutions. So we've also looked at improving the reliability of the network by basically using a hybrid, by modifying a Newton-Raphson algorithm where the initial guess of the algorithm is provided by the prediction of the neural network. And if this prediction proves to be too far from our convergence criterion, then it goes through a classical set of iterations. And you can see that illustrated in the bottom of the slide. So in this case, even if we have already a very good prediction, if it's not sufficient for us, we can further improve it and always guarantee that we have the right solution, regardless of the quality of the prediction of the neural network. So there's many things we can do with this, and this is just the beginning for us. And I think that combining physics and deep learning is certainly a very interesting and exciting research field. In our case, what we really would like to do is to improve training generalization, so we can predict, for instance, the deformation of pretty much any liver, not just one liver, and at least as a starting base. We'd like to look at graph neural networks as they provide a more natural link with the finite element method. And of course, we also want to look at the dynamics of deformable models, even though in the applications I showed, it's not necessarily important. But for a true digital twin and for our applications as well, we really want to also learn from real data. Okay, in what I showed you, we're learning from data generated from simulations. And it's, of course, essential to have these patient-specific models that will also learn from real data. So in principle, it's relatively easy to do this in other contexts because you can mix synthetic data with real data. In our case, however, although we have access to lots of images, for instance, at the time of the surgery, these images contain very poor information. And so our challenge now is to find a way of learning from, I would say, poor data or sparse data, but to do this in a way that the network still learns something and gets closer to the particular simulation for a patient. And I will finish obviously by saying that this is done in context and using the SOFA framework that we've been contributing to for a decade or more actually, and we're still important contributors, but we are really happy to use SOFA. And as part of the work I'm presenting today, there are a set of plugins I wanted to mention that we are using or developing, which would allow you to either, again, it's open source code, perform data simulation. This is the Optimus plugin. Do relatively advanced FEM simulation. This is the plugin we call Caribou, and link basically many of those things with deep learning frameworks using Python. And in near future, we'll also make available a plugin dedicated to the kind of result I showed you a few minutes ago. Now, if we have time for questions, I'd be happy to answer them. Thank you.
I don't know if there is maybe, thanks a lot, Stéphane, for the dense presentation. If there is maybe one short presentation, we're going to talk again about SOFA and the plugins later on, but if there is a question about the work that has been presented by Stéphane, do not hesitate to unmute yourself. Anyway, as we said earlier, there will be time for a direct discussion with Stéphane. It will be, if I'm correct, yeah, in 30 minutes, so at 2:30, after the two other research presentation from Christian and Maxime. Any question from the audience? I'm looking if there is. I actually myself prepared 5 different questions that actually I would maybe join your room to ask them later on, Stéphane. But thanks again, and so let's meet again at 2:30 in the breakout room for a question on this first presentation. Thank you, Stéphane. So the next presentation, yeah, will be Christian. Christian, you are already presenter. Thank you to the NAFEMS organizers that are actually helping me for sharing the screens and so on. Christian is already on stage. Can you maybe just test your mic? You are unmuted for the moment, but I guess I can unmute you if you'd like.
Yes.
Perfect. That's perfect.
You can
see and hear you. Yeah, perfect.
Perfect.
Thanks, Christian.
So thank you for the invitation. So today I will talk a little bit about soft robots and the work we do in the team for modeling soft robots using FEM. And in particular, I would like to show this work on anisotropic soft robots. So first, many of you may not know what is a soft robot. So the idea is that nowadays the robots are usually rigid. If you look at Boston Dynamics and these famous humanoid robots or dog robots, they are made of rigid parts. Whereas if you look at a human or a dog, it's made mostly of deformable muscles in particular and organs. And in general, there is also a lot of animals that are fully deformable. And basically, the emergence of soft robotics came from bio-inspiration, the fact that you be inspired by nature and create robots that deforms. And also, I think from 3D printing that also helps you to build this such deformable robots. And in particular, I will describe what we can do with the work of Sylvain Lefebvre on printing anisotropic structure. So so I will not go into too much detail about soft robotics, sorry for that, but basically one of the big challenge in soft robotics is how to model and control the soft robot, because in an articulated rigid robot, you have a small number of degrees of freedom. Usually you avoid interaction. And as you have a reduced number of degrees of freedom, the control is quite direct. And there are methods that are well known. And in the case of soft robots, the robot is deformable. So usually there is no more analytical model for the motion of the robot. The idea of using the soft robot is to come into contact with the environment. As they are soft, they are not dangerous. They can come into contact, in particular for surgical applications. But if they come into contact, it means that they will be deformed by their environment. So they behavior, you have to take into account the environment to pilot the robot. And also for control, there is the problem of having a lot of degrees of freedom, theoretically an infinity of degrees of freedom, but you have a small number of actuators, possibility of actuations. So you are largely under-actuated. So it's also a big issue in terms of control. So very quickly, some example of results in the team. We have developed an inverse model, an inverse problem for guiding the robot. So if you guide the top of the robot, you can know how to actuate the robot. Here we have a trunk robot with 8 cables. So this was one of the contribution. Another contribution with the same robot is to have an inverse problem with contact. So basically here you want to reach this point, but you have an obstacle that is not model in your inverse problem. So then the obstacle prevents the robot to go where you want. And the idea is to see how to inverse basically the model, but while taking into account the contact with the environment. So if here we measure the position of the obstacle and we use the contact here in the inverse problem to really reach the point, and you see that there is a new degree of freedom, which is the motion of the base of the robot that is activated automatically to help the robot and the robot for more to use the contact and go where it is supposed to go. Another big thing that we have done also, I thought it was a video, but apparently the video is not working. Sorry. But we have also developed a closed loop method. So basically you put a sensor at the tip of the robot, and you can avoid to have any vibration on the robot using the closed loop. But now I will talk more precisely on anisotropic soft robots. So we are using a mesostructure to design the robot. We use a metamaterial that is basically printed. So there are many examples of this metamaterial. And why it's interesting for soft robot, because you can control and program the flexibility of the material. And you can, in fact, define the good stiffness and mass ratio. Even if it's compliance, you can have something that is compliant, but with a low mass. Whereas, for instance, the silicone that was used in the previous example is a lot of mass. And you can also create unusual mechanical behavior. In this work, we also use 3D printed foam. It's a work that is in collaboration with a team in Nancy that developed this technique of printing this deformable foam. And you can basically program the density of your material, but also the anisotropy. And it's the inspiration, it's the structure of the inside of the bones. So we said, okay, let's do soft robot with this material. It's the material is. And first example that we have done is a very simple robot. So it's a robot made of 3 actuators, and in the middle, instead of having an articulated thing, you have a piece of silicon. And the idea is to control the deformation of this piece of silicon. It's a robot that we use for doing our tutorials. And here we show that we using the anisotropic form, you can basically control the torsion of the top of the material forming the shape. And how we can control that, so you can see that it deforms, but how we could control that. So, and I will then go into the methodology that we are using in the team in general. So for this particular case, an anisotropy, we are using numerical homogenization, and with this homogenization, we can construct the anisotropic constitutive law of the material. So this is also was done in collaboration with Nancy, where they already did some measurements on their foam to know the corresponding values for the anisotropic case. We are using the transverse isotropy law. And based on that, we can build a FEM model. So this is standard for any of our robots. So you can use the dynamics if necessary, but it's not always necessary. In that case, it was not necessary. But otherwise, you have the external force, the internal force, and you have a set of constraints that we are using for the actuation. For the internal force, we use a linearization for each time step. And at the end, when you have done the linearization, you obtain this. So here it's for the static model, and that's so we have a matrix A that we update at each step of the computation. This is unknown. Here the forces that are known, and the question is how to control the actuation. So the first thing you can do is impose a torque. So if you can, on your servomotor, you can impose the torque. And then if you impose the torque, you can know how it will deform. But usually it's not what you want. It's usually you want to also to do the inverse. You want to pilot the top of the robot and to know how much you move the servomotors to reach a position. And it's the important equation in that case, it's the projection of the motion in the constraint space. So basically we define one constraint for each servomotor, but also we define some constraints for the effector. And instead of solving the bit system, we use a projection in the constraint space. So we project not, so the inverse of the matrix, so it's the homogeneous to compliance. So here we obtain basically the compliant in the constraint space. And when we change the force on the servomotors, we can know the displacement we obtain at the tip. And this is a small system because it depends, as you have projected everything in the constraint space, you have a reduced system that corresponds to the number of actuators and the number of effectors you are dealing with. So for optimization, it's important, and that's how we build, for instance, an inverse problem. So for instance, here we want to control the torque on the top of the robot, and given a certain, so not a torque, sorry, a twist at the top of the robot, and define a twist, and it will find how to actuate the structure to obtain this rotation. So that's how we obtain. So here the video shows this twist in the robot and the corresponding model. And we went a little bit further on this, and we showed that we can control the kinematics of the robot with anisotropic. So we took basically 2 of these robots. So instead of having only 3 motors, now we have 6 motors. And we put them in parallel. It's quite classical in rigid robotics to put robots in parallel. But the thing is that if you do that with a silicon, in fact, you have 6 degrees of freedom in input, so you can move 6 motors. But in output, you will never be able to control here the rotation along the beam here. It's impossible to control the rotation along the beam because you have isotropic matter. But with our foam, isotropic foam, we see that if you push basically the 2 direction the beam, you can basically control the rotation along the beam. So we have shown, we have basically coupled that with the model, and with that we can show also that we can basically found the workspace of the robot. So here it's difficult maybe to see in the video, but we move the robot in any possible configuration of the workspace to see where it can go, and have the envelope of all the points that are reachable, so you can see here. And then so it's really allowed to have an analysis of the design. Basically that's this. So I wanted to show you this anisotropic soft robot because I think it's a very funny way of building robots. We have shown that in fact you can what is really new in robotics is that you can play with the material to change the kinematics, and it's completely new in robotics. It's maybe obvious for people that are doing structural mechanics, but usually in robotics, when you have defined your kinematics, it's never influenced by the material you are using. So we have demonstrated that with the 6DOF parallel soft robots. We see that modeling is a key point. And now we are working on the calibration because when you print the robot, you have some difference between the material and the model, so the printed robot and the model robot. So we want to have a way of calibrating the model, doing design optimization, and in more future work, longer view, we would like to have a smart material where we can have influence on how we print the robot, but also adding sensor, electronics, actuators inside the robot. That's it. I would like to thank also Phoenix Vanessa and Olivier Goury who participated in this work. Thank you for your attention.
Thanks a lot, Christian. Sorry for the audience. Indeed, when you were actually displaying videos, I guess it's maybe the servers, the WebEx server behind. But when there is in parallel videos and the sound seems to be sometimes affected. So hopefully, I guess it was a too good video quality that was maybe affecting the stream. So sorry for that, guys. You can actually maybe, I think most of these videos you'll be able to find them on, or at least some of them you'll be able to find them on the YouTube channel from the Defrost Inria team. So I'm going to copy paste the link right after. Since we're already 2 minutes late, it's not a big deal. We're gonna switch to the next session. Keep your questions for in about 15 minutes. So get ready. You can really do not hesitate to also write questions while the presenter is actually highlighting his research or his work. And at the end of the presentation, I would be delighted to just forward the question if you don't want to unmute yourself. So thanks again a lot, Christian, for this presentation. See you in 15 minutes for the questions, for the question session. So as you can notice, we moved from simulation for surgery, then simulation in soft robotics, so a completely different purpose. And that can within the robotics domain be used for automatic design, adding anisotropic to the robots. And now we're going to go towards medical devices with the SimCardioTest project, a European project presented by Maxime Sermesant. The floor is yours, Maxime.
Thanks, Hugo.
Thanks.
So hello, everyone. So to start with, I mean, Inria has been very active on cardiac modeling for the last 20 years with a series of internal and external funding. And one of the specificities of this work was that in addition to setting up complete cardiac models, including electrophysiology, anatomy, solid mechanics, and blood flow, we also focused a lot of work on the personalization. So a bit like what Stéphane showed, I mean, how do you estimate the parameters of such models so that they really represent a specific patient and not a generic heart? So as you probably can imagine, modeling any living tissue is always difficult due to the complexity in knowing really the constitutive laws and how you can describe mathematically such living systems, but also by the inherent variability from differences between people and also different times, adaptation to effort, for instance, for the heart, if you start running or if you are lying on your bed. And then once you deal with this modeling problem, then comes the problem of how do you estimate the parameters? How do you, from sparse and noisy measurements, control such parameter estimation? So in terms of cardiac models, in recent time, I mean, the trend was mostly to go for more complex models. I mean, adding more equations to include more phenomena in such models, thinking that if you are more realistic in terms of the number of phenomena, then the global model is going to be more realistic. But given all the complexity of the equations and how to solve these on very fine meshes, we believe that maybe another approach where you start more from the data you have, which will be guiding what you can estimate as parameters, and then design a model which can be compatible with such data, could be maybe more interesting for more clinical application of such models. So I will present you some results on two main pathologies, so cardiac arrhythmias and heart failure. So first, for cardiac arrhythmia, so that's a pathology of the electrical part of the heart, when this electrical wave that control every heartbeat gets into a chaotic mode. So there is a therapy which is catheter ablation, where you can go inside the heart and burn the cells which are responsible for such pathological behavior. However, it can be very lengthy, I mean, 6 to 8 hours, and there are still a lot of recurrence. So people have to come back for another interventions because the success was not at the first intervention. So one idea is to build patient-specific models from the available data so that you can test and validate interventions before performing them actually on the patient. So to do this, there's again a lot of different models, and we tried to see where we could go with the simplest models possible. In case of wave propagation, this is the iconal model. So the iconal model is just simulating the time of arrival of the wave and not any electrical potential. And we could show that using such model, you can have a very fast simulation of the propagation of the electrical wave, only based on the imaging data. So for instance, here we show how we're using the thickness of the heart that can be measured directly from CT imaging. We can estimate the propagation parameters of such models, and in few minutes, initiate the activation. And we could compare this to invasive measurements from catheters with a very good correlations between the measurements and the simulation. So then we move to a more complex simulation scenario where we want to simulate the whole procedure of ventricular tachycardia stimulation, where cardiologists put a catheter in the heart and pace it faster and faster to see whether an arrhythmia will develop. So for this, we need more complex models, so using reaction diffusion equations, for instance. The Mitchell-Schaeffer model is a two-variable model, which is quite well suited for such simulations. And we could show that by estimating parameters from some measurements, we could also predict the arrhythmia that was induced in this patient. And if we compare in 2D, which is maybe simpler, when we project the activation, we could see that on the left, that's the activation of the pathology in the patient, and on the right, that's the one which was predicted. It's very similar in terms of circuits. So what is the pathway that will be followed by the pathology? And we could do this also in another patient, but it's still very long procedures to estimate these parameters and simulate such models. And the data we used here was quite invasive because we already needed invasive measurements from catheters to do such patient-specific models. So we tried to move away from such invasive data and use only imaging data. And for this, the idea is to use directly the wall thickness, as I already mentioned. So when the heart is very thin, it's probably that there was an infarct, and then the muscle is much thinner than it should be. And so we propose to use the lattice-Boltzmann method to simulate the reaction diffusion equations on the Cartesian grid of the image directly, and learn the relationship between this wall thickness measured in images and the electrical parameters of the model. And we could show that it enables to do a realistic simulation of the electrical activation in the heart. And here you can see the protocol, stimulation protocol simulated. At some point, it starts circulating around the black area, which is the infarct area. And that's when we predict a given ventricular tachycardia. And for this patient, the same tachycardia was measured with catheters. So here, in a completely non-invasive way, just using imaging data, we could predict the pathology in such a patient-specific manner. And I mean, the beauty of modeling and simulation is that you can be much more extensive than what you can do in a patient. So here you can take like 100 points on the heart and stimulate extensively from these 100 points. And how many of these really generated arrhythmia, which can be a measure of the risk of sudden death for such patients. On the mechanics, we are looking at heart failure, which is the pathology when the heart is not able to pump enough blood for the body. And there is a very interesting therapy, which is called cardiac resynchronization, where you implant a pacemaker in order to resynchronize different parts of the heart so that they really contract at the same time and be more efficient in ejecting blood. But there's still 1/3 of the patients who don't have any improvement even after having such pacemaker implanted. So there's still a lot of room for improvement in order of selecting the right patient and optimizing the therapy for every patient. So again, we use the same approach of personalizing the model to the data. So having 3D imaging and measurement on the electrophysiology, we can generate a patient-specific model of this patient heart. And then we can virtually pace the heart if we were implanting a pacemaker and see how much the pressure changes in the heart. So how much benefit will the patient get from such therapy before implanting any device. So these are the works we did, but still, again, it was very long and very sensitive to noise to have very complex models integrated on the heart scale and with the electrophysiology, with the mechanics. So we proposed to have a more compact model for mechanics, because actually in measurements, what you get from imaging is mostly regional. So you don't really know a point-by-point motion, but at the region level, a few centimeters, you can measure the deformation and the displacement. So we propose to have a finite element approach, but which relies on regions, where for each region, only an affine transform is used. And then there is a mixing function in order to compute deformation in any point. So we could show that this drastically reduces the number of degrees of freedom, but we believe it can still reproduce quite realistically the cardiac motion. So we are trying to see if such reduced models can be more efficient and more robust when estimating parameters from clinical data. But the next step for us after working on patient-specific model and trying to reproduce pathologies and therapies was to see, can we go further, even use such models in order to help developing new therapies? So there was this call from Europe about accelerating the uptake of computer simulations for testing medicines and medical devices. And so we submitted the SimCardioTest project to demonstrate the feasibility and effectiveness of such approach for cardiac devices and drugs. And there's, of course, an important work of interactions with regulatory bodies and physicians and companies, so that such in silico approach is really accepted by all the stakeholders. And we hope such approach can also help healthcare innovation pace and get more therapies for the patients. So the approach is to develop a cloud-based platform so that in addition to the current experiments and clinical trials, it's possible to test in silico using this cloud-based platform different design of devices and drugs, and get from these simulations enough information so that it can support the certification of the devices. So we have three use cases. The first one is on pacing leads and catheters, where we gonna use a mix of in silico and physical simulator so that we can validate the navigation of these devices. We want also to be able to simulate the capture. So when you use a pacing device, there is an energy threshold above which the heart will actually be excited. And it's quite difficult to predict this on simple experiments. So we believe that detailed simulation of cardiac tissue can help. And also the fatigue. I mean, these devices are implanted for 10, 20 years in the human body. So it's very important to be able to predict the fatigue and the risk of rupture, but it's also difficult to test in realistic conditions with a motion which is close to cardiac motion. So again, a mix of physical soft robots like what Christian presented and simulations could help us providing better testing. The second use case is about thrombus formation and the risk of stroke. So in the atrium, there is this appendage where the thrombus can be formed and then has a risk to go to the brain or anywhere in the body. So there are new devices to occlude this appendage so that there is no risk of thrombus from this appendage going to the body, but it's still a complex device, and to know which patient will benefit from it is still difficult. And how to optimize the positioning and the design also of such devices is very difficult. So again, we'll use in silico approaches to help the design of these devices and predict the response to the treatment. And the final use case is about cardiac drugs. And there is a very important topic of potential efficacy of these drugs, but also safety and potential cardiotoxicity. Because any drug that impacts the electrophysiology of the heart can increase the risk of sudden cardiac death. So there are ways to test in silico how much a drug impacts the electrical potentials and verify that it's safe to be used. And also, for instance, in oncology, I mean, there are different chemotherapies which were shown to have an impact on cardiac function. So we would like to see if in silico approaches can help also predicting such cardiotoxicity. So the ambition is to create this unified and standardized platform where people can connect and test different devices and drugs. So as you know, I mean, I believe the combination of in silico approaches and high performance computing can really help in this approach. So there are still improvement to be done on the modeling part. So for the first years of the project, we're going to finalize the different models we're going to use. And then we're going to integrate them in a cloud-based platform and also propose more data science-based approach to explore the resulting data. If you do a real clinical trial, you don't have many output values to analyze. But if you do an in silico trial, you've got a lot of output from the simulation, so you can explore this for maybe discovering new biomarkers. This is the timeline of the project. So we started on January 2021. So we are now finalizing the different models and getting into the stage of verification and validation of these models. And then we're going to run in 2023 the in silico trials, and then focus on the exploitation and support of regulatory bodies for the last year of the project. We've got a consortium of 10 partners throughout Europe and also a US partner, Boston Scientific, and a very interesting advisory board with people from different institutions and people from the FDA and the European Medicines Agency to help us with the regulatory aspects. To conclude in the impacts, so that we hope to have an impact through such project on clinical trials to help the adoption of in silico approaches for clinical trials, and maybe think differently on how things can be tested along the life cycle of a new device. On the regulatory system, there's still a lot of work to be done in order to be able to use more and more in silico information when going through approval, and we believe that constant interactions with regulatory bodies should help in co-designing how in silico can help such aspects. And finally, I mean, we can see that the rhythm of new innovations in healthcare is really slowing down due to the huge cost of design and trials of new products. So we hope that the in silico approach will help in reducing the time to market and helping designing these new devices and drugs. So to conclude, I mean, here's all the partners of this project. As I said, we hope that it will help innovation in medicine, and I mean, there are many other activities in such aspect, and with the VPH Institute and the Avicenna Alliance. I mean, I think there is now a good momentum to have really an impact of the in silico approaches in healthcare. Thank you for your attention. I'll be happy to discuss this with you.
Thank you, Maxime. Thanks a lot. So I added also in the chat the link towards the SimCardioTest website if you want to take a look at it. I forgot to before also mention I mentioned the YouTube channel from the presentation, the previous presentation. So just a detail, Maxime, about the platform. At the end, the objective is to get it completely open and available for any company that would like to create its own simulation in silico, or how would it work to access it actually?
So there is a company actually existing called In Silico Trials,
okay,
which is developing a cloud-based platform for such trials. So the idea is that we're going to integrate in their cloud-based platform the different models developed in the project. So the idea, the first way of exploiting the project will be through their expertise in setting up such a platform. But then there can be other ways to use it. So it could be also directly in the R&D departments of companies. I mean, not ways to use it is still very open.
Okay. Thank you. Is there any other question else? I mean, feel free to post it in the chat, as I already said it before. So don't be shy. I guess I mean we are more than we are more or less constantly 85, 90 from what I can see here. So do not hesitate to post any question that you can have in the chat. Thanks again, Maxime, for the presentation. I'll let anyone the time for typing the question in the chat if needed. And in the meantime, here I am. All right. Just to show you again the agenda. So that was for the overview for this first research project session. First, about simulation and using Bayesian inference and data-driven simulation in general. Soft robotics with Christian and the SimCardioTest project that Maxime just presented us. We're going to have, therefore, 3 different breakout rooms, so 3 different sub-sessions in which you can actually ask directly the speakers, anything you want about their work and their presentation. So I'm going to split the main room into 3 different rooms, and you'll have the choice actually to go in any room you'd like for the next 15 minutes. Yeah, 10-15 minutes. We're going to restart at 2:45. All right, so let's say rather 10 minutes. Assigned participants, and you're going to be free to choose the session. So there will be 3 sessions. That's it. And there you are. So we're going to start the second part of this afternoon that will be focused not anymore on research, but as you might have noticed, most of those research projects and research teams, research topics, they were actually based on some open source platforms. And we're going to detail 3 of them this afternoon, which are 3 among the many open source projects and softwares developed at Inria. We're going to start with one that is called MedInria, which is an open source solution for medical image processing that will be presented by Florent. Then we'll talk about SOFA for physics simulation and Pinocchio for rigid multibody dynamics in C++ and Python with Justin. And again, we're going to have a breakout rooms, so times for discussion in specific sub-rooms. Do not hesitate to really just click and join any room you'd like for discussion. So I'll let Florent take the floor. Just there it is. Florent, you should be able now to again share your slide and start the presentation of MedInria, the open source solution for medical image processing.
Thank you.
Perfect. We can see the slide.
Welcome to the MedInria overview. Let's start. MedInria is a platform. Is a software platform that provides medical image processing and visualization. For visualization, we are able to render 2D, 3D, and 4D. For 3D images, MedInria has volume rendering and multiple surface rendering, known as the acronym MSR. It can also display mesh and fibers. The software provides many classes of processing, like segmentation, meshing, registration, filtering, different tensor imaging. Now, I will give a quick focus on some interesting process for simulation. Segmentation tools offer the possibility to generate mask and labeled data, which can be very useful for AI processing. Meshing tool offers the possibility to create a mesh from mask and manipulate it. You can therefore rely on MedInria to build your medical image pipeline. Well, we are developing MedInria as a software platform aimed at providing research clinicians with medical image analysis tools coming from research. This software will progressively include developments coming from 3 of the major teams in medical image analysis at Inria: Carpentier, Avicenna, and MPen, making it a future major diffusion platform for our research developments. Each team has a specialty: diffusion imaging and EEG for Avicenna, imaging biomarkers for understanding and monitoring brain and spinal cord pathologies for MPen, and cardiac modeling and computational anatomy for Perrin. MedInria goes today beyond Inria. It's a platform for international research teams, clinicians, and collaboration with the industry. The community are polarized between academics or medicals and startups or spin-off. We are hosted and supported by Inria, and we are in close relation, for example, with the APHP on different projects for medical image segmentation. Many startups or spin-off use or rely on MedInria, like TheraPixel in heart and rebrain. MedInria takes place within the InriaSoft initiative. InriaSoft aims at promoting open source technology from Inria by building open source consortiums around its technologies. all MedInria consortium members have a right vote on the governance. Inria and EHU Lyrics are two consortium members. APHP is a close clinical partner with which we already have ongoing projects. And we are getting stronger and stronger relationship with recent partners. Earlier, I presented you the different process and algorithm available in MedInria. The MedInria home interface groups together each type of process. These are easily accessible in different workspaces. Each button in this interface represents the access to one of these workspaces. Now we look at a visualization workspace in a short video to exhibit multiple data types in 2D and 3D. At first, we drop an MRI brain image. We custom the image intensity. We navigate through the MRI slices. We had a mesh on overlying. We switch the orientation. And now you can see a 3D rendering. You have the MRI with a MSR representation and the mesh in 3D. We drop fibers data. We have a good superposition of fibers, mesh, and MRI. Come back in 2D, and finally we add a mask. You can see the mask on the right. Now we look at visualization workspace in a short video to exhibit 4D MRI and superpose 4D mesh. You can see the heartbeats. We drop a 4D mesh, not on MRI and simulation mesh are beating together on 2D. Now we switch in 3D, and you can see the mesh and the MRI beat together. Now a quick example of registration. For the first two images, you can see the pointer on the right of the image is not pointing the same brain area. Since the two images are not registered. Now you have a superposition of the two MRI. The first one is in red scale, and the second one is in green scale. By using linear and nonlinear registration available on MedInria, we can align the two images. Here it's a linear block matching algorithm. Here you can now visualize see the space coordinate in both images, thus corresponding. The cross is indeed pointing to the brain area, to the same brain area. The registration was successful. The superposition is pretty good. I talk about the current development of MedInria. We have 4 main current developments about segmentation, Python scripting, improved plugin accessibility, connection with different type of data source. We have about the segmentation, we have a new segmentation model. This model was developed in partnership with the APHP. Thanks to the participation of medical doctors, it offers a great user experience. This module is already used in a custom version for the APHP and will be present very soon in the common version. For the Python scripting, we are finalizing the integration of Python for the opportunity to script MedInria and include the quick development in Python. In a near future, the Python bindings makes possible to integrate the integration of deep learning pipelines or to delegate computation to GRID. Another development in progress consists in completely renewing the system of plugins to facilitate the development of new features. This will culminate in the creation of a complete SDK. And finally, MedInria is in the process of changing the paradigm for its data sources. Instead of working on local data, we are developing an extensive connection system to different data centers like packs, databases, cloud file system, etc. This is to be in perfect harmony with the current and the future expectation. Thank you for your attention. You can download MedInria on the MedInria website. Each platform are available like Windows, macOS, and Ubuntu. Or join the MedInria project on GitHub under the project is under BSD license.
I'm gonna add the GitHub link directly in the chat for you, Florent.
Okay.
Thanks a lot, Florent, for the presentation. From what I know, so MedInria is the software used actually in the SimCardioTest project that has been just before presented by Maxime, right? For medical imaging, medical image processing. Is that correct?
Maxime.
Yes.
Okay. Okay, perfect. And maybe for also the information that you gave is that, you know, inputting medical images within MedInria allows you to then after segmentation, even registration if needed, basically after processing your images, you can output them as a mesh and use those mesh information inside your simulation, right?
You can create a mesh based on mask, and the mask can be obtained by segmentation and registration.
Okay.
And you can export data as many common formats for medical imaging.
Perfect, thank you.
Nifty or MHA.
Okay. MSH is good for us. I mean, that's what it's among the one we use indeed. Thanks for. Is there any other question? Otherwise, as for the first session, the research-oriented session for this open source platform session, we're going to have a time for discussion in 30 minutes from now. So it's going to be again at 3:30. Do not hesitate. So 3:35 maybe. I guess we have 5 minutes delay. If you have any question, do not hesitate to drop it in the chat, as I already mentioned here. Otherwise, I'm going to move on. If you have on-the-fly question, do not hesitate to ask. Florent is staying with us, so do not hesitate to ask that in the chat, or join him directly in the breakout room in 30 minutes. Thank you. Thanks a lot, Florent, for the presentation.
Thanks.
All right. Share. Now you should be able to see the second presentation that I will be doing. It's about SOFA. SOFA, so at first I'm glad to be here among you and having the opportunity with this NAFEM Day to present you SOFA. SOFA, it's a project around physics simulation, and we like to present it as a good solution for collaboration, prototyping, and innovation in computational biomechanics. It's a project that started back in 2006 at Inria, this French research institute in computer science. And since the very beginning, it arose from the need of several research teams to collaborate around one common framework for physics simulation. And today, when we are getting asked what is actually SOFA, the definition that we give is the following, being the open source reference for interactive simulation, physics simulation. So as a physics engine, SOFA does include models like mechanical models, algorithms describing the physics around us, and it's mostly including soft and rigid body dynamics. That's actually why we gave you just before, like in Stéphane's and Christian's presentation, soft robotics application, as well as medical simulation, whether it is used for training, planning, or guiding during an operation, a surgical operation. So, but that's really the main topic of SOFA, soft and rigid body dynamics. Various fields, as I said, I've already been investigating: medical simulation, soft robotics, which is way more recent, like just a few years ago. That's really a rising topic for us. Animation, like computer graphics, and biology. Since the very beginning, the development of SOFA followed these 4 keywords as a concept. First, it has to be flexible. The way you are defining your simulation using XML script or Python scripts now had to be flexible, efficient. So we wanted to have an easy design of simulation. Second, we wanted to have a modular architecture. This is actually because we are following an open core architecture with an open source core and optional plugins around that you can activate or deactivate. Efficient, using multi-threading, GPU computing, efficient enough so that you can actually have interactive simulation so that the user can get into the loop, so that objects can interact with another and the simulation can still remain interactive. So that's the 4 keywords: flexible, modular, efficient, and interactive. The source, so the code structure, as I said, is following the concept of open core. You have a core of code written in C++ under the LGPL license, meaning that you can download, use, modify, and even make a product freely based on SOFA. We are providing regular releases from this open source core, and around this open core, you have optional features. That's what we call the plugins. That's where research teams are developing their algorithms. That's where companies are developing their algorithms, independent developers. Basically, anyone can create his or her own plugin, and obviously, on those codes, the license is free to define. SOFA is over all platforms, macOS, Windows, and Linux. And when you get SOFA, you also have access directly to an open documentation, whether it is user-oriented or developer-oriented. For developer documentation, is what we call API documentation, using based on Doxygen. So if you want to start with SOFA, two ways. You can download it, either you can download the binaries, so precompiled version of SOFA, or you can download the sources that you will need in a second step to compile for your machine or for your server if it's on a server. So that's the different steps for compiling SOFA if you are working with the sources, and everything is explained in the documentation. So let's see a bit the features of SOFA. What is inside SOFA? Obviously, as all physics engine, simulation engine, you're going to have a way to load meshes, and that's what we call loading topologies, how how many elements you have, how they are connected, so their connectivity. That's what we will use, especially for the discretization in space using the finite element method, since most of the algorithms in SOFA are using FEM. Different topologies, and that we will see in the hands-on session. I'm going to open SOFA and show you that very shortly, but we are decoupling completely what you can actually visualize from where the physics is actually computed, so the volumic geometry on which you are actually computing and integrating in space your physical law, and also the models that will be used for collision. We can use different models for each of those physical, visual, and collision models. You have a collision pipeline to detect and respond to collision, and you have all the physics models and algorithms like solvers, integration schemes, and elastic, hyperelastic models, as Stéphane already mentioned before. That's for what is in SOFA. And around SOFA, you have plenty of plugins, actually more than 100. I think today it's actually more than 150 plugins for basically everything. So we have an online marketplace. You can just check out here if there is a plugin of interest for you. If you don't find the plugin of your dream on the marketplace, never hesitate to contact us, because some of those plugins are sometimes private, and we can make the connection between you, whether you are a company or researcher, with the different teams developing the plugin. Okay. Here are a few examples how to use SOFA within a Python environment, using SOFA within Unity 3D or Unreal Engine. That's done by a consulting company called Infintech 3D for using SOFA and having advanced rendering. Model order reduction, dynamic topologies, again, Infintech 3D, soft robotics, and beam modeling. Just few examples that I thought was of interest. So a very short hands-on session. So I'm gonna share another window here. I'm gonna share a SOFA window just for a second here. I opened a scene here in SOFA, and what you can see here is the typical SOFA view live here. So you have we have an object. I'm gonna just show what. Yeah, we have what we like to use in SOFA, a lever. This lever is deformable. I can actually pull on it and so on. That's the user interaction I was mentioning here. It's a very coarse model, but anyway. And I mentioned before, we are decoupling the different visualization model, the physical model, and the collision model. Indeed, here, for the rendering, you can see we are using a triangulated mesh, but just a surface mesh. That's the one we are using for rendering. But the one for rendering is actually completely different from the one used for the physics, for the mechanics. The mechanics is computed over this volumic tetrahedral mesh here, this blue mesh. And finally, for collision, we are not using like a mesh, a surface mesh, but instead we are using a series of spheres that will detect if an object is colliding with those spheres. So you see, this way, we are really defining and deciding where to put the computational efforts in SOFA. And in Python, you can even do more, because here I started the simulation, and I can even just, like with keyboard interactions or any kind of interactions, add new objects. Those objects here, the rigid spheres, they were actually not existing at the beginning of the simulation. You can see here, they were not existing. But as soon as I'm here just with a keyboard, but it could be any kind of triggering effect, you can create new objects or change the physical properties of objects while the simulation is running. Okay. Okay. So I'm going to get back to the slides and conclude for this part of the presentation. There we are. So during the 15 years of development of SOFA, there have been more and more developers, so daily contributions. And now the way we are actually working is following a strict protocol, like we are working with a versioning system, Git, hosted on GitHub. So you can find all the code of SOFA at this GitHub address here. And to contribute, people are actually making what we call pull request. It's a proposal of contribution. It is peer reviewed by developers every week. And this allows us to follow a stable development process. And that's what gives the stable releases every 6 months. Who defines the roadmap? The technical committee, where we have partners deciding with us where the software is supposed to go. What will be the future developments? Among these 15 years, actually, just in the last 10 years, we have also 7 startups that have been created around SOFA. So that's the reason why we decided with this ecosystem to create a consortium, open source consortium, to talk about the maintenance of SOFA, coordination of the development, taking care of the animation of the community, and ensuring the growth of the ecosystem as a third party at Inria. That's for the partners, and we have donors like the consulting company, Infintech 3D, Harvard University, Harvard Medical School, and University Verona, University Milano as well. That's for the technical members that are actually helping us to design the roadmap and the future of SOFA. If you want to see more examples of SOFA, we can meet in the breakout rooms at the break right after. In a break, I'll be in the room 2, Florent will be in the room 1. And for the take-home message, do not hesitate to download SOFA, test it, use it for your own purpose. You can use the doc, get support freely from the community. We have also training sessions that you can have access to. And really, the meeting point I would like to give you is really end of November, where we have a full day dedicated on SOFA. That's what we call the SOFA week, meeting the researcher and the companies, discovering the latest progress on SOFA and networking. So thank you for your attention. If you have any question, I would be pleased to answer them. And we are still a bit late. I did not succeed to get faster. But let's meet in the next breakout session. If you have any question, I would be happy to take them. Otherwise, see you at 3:30 for more questions. I'm looking at the chat. I don't see any further question here. So yeah, I'm taking back the other hat, the one from just animating. So that's for the 2 first presentation about MedInria for medical imaging, medical image processing, SOFA for physics simulation. And now we are getting back to robotics with Justin that will present Pinocchio, and I guess not only Pinocchio, but Pinocchio, the platform on which they are developing their simulation and modeling of robots as well at Inria. So can you share already your screen, Justin?
Yes.
Perfect.
Is it fine? Can you see it?
Yeah, perfectly. Yeah, maybe you can make yeah, that's perfect. Full screen. Great.
Okay.
Thanks. The floor is yours.
Okay, thank you, Hugo. So thank you very much for inviting me for today. So today I will just briefly present you what is Pinocchio, which is in fact a universal framework for control and simulation in robotics, and mostly currently for rigid robots, but we are moving towards soft robots because this is a new trend for us. I will start by a motivation example, this one. So I think everybody has seen this video so far. So this is a very strong robot, but very rigid. And what it makes this robot very robust and efficient is mostly due to the fact that he is able to anticipate in the few upcoming seconds the wall motion. And for that, they are using optimal control, model cognitive control. And what we need to do for that is really to compute in a very efficient manner the dynamics of the robot interacting with the world. And for that, we need a good and strong physical engine for doing that, which is able to compute at many kilohertz the dynamics of the robot along the life of the robot. And so the dynamics of this robot is governed by the so-called Lagrangian dynamics. And so the Lagrangian dynamics, I mean, everybody knows a bit these equations, but this is another way of formulating the dynamics along with Newton formulations. So here we have a polyarticulated system, with gravities, And we have here the equation mass time acceleration plus Coriolis and centrifugal effect plus gravity is equal to the torque applied by the motors and also the external forces. And so we put in actuation the whole system, and this system is falling if we don't have any gravity terms here. But so we need contact interaction, we need constraints if we want to totally control the system. And the purpose of Pinocchio and the purpose of many algorithms in robotics is really to compute in an efficient manner these equations. So either in a forward mode, so what we call forward dynamics. So given the position, velocity of the joints and the current torque applied on the joints and the contact forces, we want to compute the acceleration of the joints, and the reverse, which is called inverse dynamics, where from a given output trajectory, we want to compute the torques that produce the motion. And this is by either inverting or computing the forward of these equations. And so the whole motivation is to exploit at best the sparsity pattern produced by this equation of motions, which is mainly lying within these quantities where we have a sparsity pattern, which is induced, in fact, by the kinetic tree that is very proper to kinematic chains like humanoid robots that we have seen so far. And all these equations and all the algorithms that are very powerful to compute and to solve this equation are all registered in this book done by Roy Firestone more than 30 years ago, and which is still up to date at some point. And so we took inspiration from this book to write Pinocchio, which is an open source and efficient framework, so under the BSD2 license, which implements most common rigid body dynamics algorithm. So written in C++ for efficiency, but also coming with Python bindings. So we have here the GitHub webpage. But now I will try to show you what is the historical aspect of Pinocchio and how we can use it. So at the beginning, I did my PhD in Toulouse, so at La CNRS, working in the Gevito team, which is dedicated to legged robots. So we have Achapito robots and Talos robot on the left picture. And so in 2015, during my PhD, we started the development of Pinocchio because we need efficient frameworks to do the control of these robots. And so this is where the story starts. And so now I'm in Inria Paris, and we are still collaborating together with La CNRS to develop Pinocchio and to put more features along time, so like derivatives, contact dynamics, and now what we are doing is to build a differentiable simulator, and we are trying also to learn the physics from sensor data in order to get a better simulation. So currently we have many users coming either from academia or from industry. So we have Airbus, PAL Robotics. So PAL Robotics is a European leader in building robots in Europe. We have Wondercraft, which is a startup in Paris, which is building exoskeleton. We are working with Bosch AI, and also with Arrival and Covariant, which are new like spin-off working around the AI for either automotive industry or AI for manufacturing. So the Pinocchio library, at first glance, is implementing the classic algorithms of in the literature. So we support a large number of joints of topology to depict the kinetic tree of our system. We exploit at best the sparsity of the system using the so-called Firestone algorithm. We implement the classic algorithms that I've mentioned so far, so forward inverse dynamics, but also more advanced rigid body dynamics algorithms that we are currently developing. So we are also able to deal with Lie group formulation, which is very essential if you want to work on the real geometry of your problem. We are also implementing analytical derivatives, as I mentioned, which is very essential if you want to be fast to compute predictive control solution to drive the motion of your robot. And this is what makes, for instance, Atlas robot from Boston Dynamics working very agile and acrobatic and performing acrobatic maneuver. So we are still also able to do automatic differentiation if we want to differentiate the whole pipeline of equations, to do also source code generation now if you want to embed some codes within robots and to avoid to have a big computational infrastructure. So for fast prototyping, we have Python bindings, we are multi-thread friendly. We are also able to do collision detection, and so we collect all the essential features if you want to build a simulator on top of Pinocchio. So there is now many simulators that are built on top of Pinocchio. And on our side, we are developing this new simulator also with efficient algorithms. So the whole aspect of Pinocchio is that an algorithm is always templated by the scalar type if we want to override it and to do autodiff, for instance. And we have this notion of model and data, and we always still split these quantities. So model are constant quantities, which are fixed, while data are quash quantity, which are very efficient being used by the CPU in order to cache all the intermediate computations. And these things makes the framework very efficient. So we are much more faster than the state of the art concerning the rigid body dynamics algorithms. And in general, we don't have any memory allocation during runtime. So it means that we can really trust what we are doing, and we don't have any. So avoiding memory allocations is very fundamental if we want to do kilohertz control of robots, which are essential for locomotion. So now Pinocchio in action, very simple. So this is just some benchmark that we have performed like 4 years ago on KUKA robots and on Atlas robots, the first version. So the timings now, we can all divide them by at least 2 or more. But for solving the inverse dynamics or forward dynamics, it's only 0.8 microsecond or 2.8 microsecond at this time. And if we look at generation, what we can see on KUKA robots is only 0.2 microseconds. So it means that we can perform like 5 megahertz simulation per second. So this is very essential. For instance, if you want to do a reinforcement learning, or if you want to do model predictive control on your system, you really need this feature to be efficient and to avoid to waste time in these computations. So in addition, we have been working recently on improving all the rigid body dynamics algorithm to deal with constraint systems. And for that, we have used what we call proximal reformulation. So I won't go into these details, but if you want more details, you can go to this paper. But what I wanted to say is that there is still some research to do, and we are trying to do this research together with the implementation within the Pinocchio library to make it available for the world community. And I think this is essential if we want to have fast transfer of our research towards the industry, and because new robots need this feature. So this is some benchmark of the timings of this new algorithm. So in grid, this was a former implementation in Pinocchio, which was already state of the art. And now in orange, what we have is the timings of the new implementation, which is exploiting at best the sparsity pattern of the problem. And so what we can see is that we are able to divide at least by 2 or more the computations by just using this new kind of algorithms. So this is, for instance, some animation of using this algorithm on most standard robots. So here we have a quadruped robot, we have the Talos robot from PAL Robotics, and we have also the Cassie robot from Agility Robotics. And both these robots suffer from contact constraints or loop closure constraints like this one, like the Cassie robot. And so all our solutions are able to run on this platform at in a very efficient manner. And so the whole goal of Pinocchio is very able to be versatile. I mean, to be able to operate on all the rigid body robots that we have currently. So in addition to that, so as I mentioned earlier, if you want to do numerical optimal control, or if you want to do RL, you need to be able to compute derivatives. And for that, we have implemented in a nice manner all these derivatives within the framework, which means that we are able to evaluate at the same time the evaluation of the function and to compute the derivatives without too much additional computational burden. And this is very essential if you want to be efficient and to get some gradients information that are essential if you want to do first order or second order optimization methods. And so here, again, this is some timings. So if we were using, for instance, finite differences to compute the power dynamics derivative on the last, for instance, it will take, for instance, more than 400 microseconds, while if you do identical derivatives, it's 10 times lower. So again, these timings came from 2018, but now with new computers, with new implementation within Pinocchio, we are able to divide by 2 at least all these timings. And so this is an illustration of of using Pinocchio for optimal control. So this is done by Carlos Masteli, and this is an athletic motions with the Talos robot. And so this motion is it's very easy to compute these motions thanks to these derivatives. So what is the future of Pinocchio? So what we are planning to do is to port Pinocchio on GPU and FPGA code source generation, because a lot of people are asking for this feature, and this is very essential if we want to have embedded model within robots and to increase their autonomy. So we are working on the more constrained dynamical systems. We are building now an open source robotic simulator in order to replace Mudoko or Bullet, which are not suited for our research. So we are working mostly on a full differentiable simulator, which is very essential if we want to learn new contact model, if we want to learn to improve the quality of our simulator coming from sensor data. And now we are also working on supporting biomechanical systems for biomechanics, and working on cogeneration of robot controller and so on. And also, we are also trying to improve all the collision detection algorithms that has been using so far by the community and through the FCL algorithm. So, and in the future, what we are planning to do, so we have new software also coming in front of Pinocchio. So we have efficient and differentiable convex optimization solver for control and learning. So we will provide that soon. We are working on a new software for online model predictive control of robots, and also, as I mentioned, we are working on the differentiable simulator. So which is, I think, a feature which is missing inside the world communities, and which can also benefit to SOFA framework, for instance, to learn contact models. So thank you very much, and I'm very pleased to take questions.
Thanks a lot, Justin. Is there any question in the audience about Pinocchio and all the possibility and future possibility of Pinocchio? As we said also earlier, you can definitely post everything in the chat. What I suggest now is that if there is, so I'll let you just 1 minute, maybe if you need the time for asking questions. Otherwise, we're going to move into, just like before, breakout sessions. So you'll need to decide in which room to go. Again, room number 1, it will be. So I could share the slide again, just to make everything super clear. There, you should be able to see it. There you are. So room number 1 will be for MedInria, room number 2 for SOFA, and room number 3 for Pinocchio. We're going to create the breakout rooms right now, and just feel free. So there we are. All right. It should be fine now. Okay. All breakout rooms should end in 5 seconds. So now we're gonna restart the main room here. Perfect. And I'm gonna share here just the window to present the third and more or less last session, because they will be on top of the session which is here from Thierry Marchal. It will be more oriented on industrial applications. We'll start with a talk from Yinoussa about Oticon Medical and how simulation is actually used for implant testing in ear surgery. In a second step, we're going to have a presentation of PrediSurge from David, presenting a simulation of blood flow for the design again of implant for this time cardiovascular devices. Okay, so we should give the floor to Younes. Younes, are you around?
Yes.
Perfect. And are you able to present? I mean, to share your screen already?
I want to see. Так.
Great.
You have my screen?
Yeah, perfect.
Okay. Can I start? Or?
Yeah, go ahead. The floor is yours.
Hello, everyone. I'm Younes. I'm from the first team. And the work I want to present here is the collaboration we are doing with Oticon Medical. It's based on cochlear implant insertion, the simulation of cochlear implant insertion. Okay. According to the statistics of the WHO, over 400 million people suffer from disabling hearing. Among them, we have 34 million children. And if we come back to France, it's 10% of the French population so about this disease. Today, we don't have a specific treatment. The first solution, if you have partial deaf, is to use the hearing aids, and for the totally deaf, what they do is the surgery, the cochlear implant surgery. What's cochlear implant? How it works? Unlike to the hearing aid, where you have to amplify the sound, for the cochlear implant, you have to operate and you install this machine, which is this device, which is contains the microphone, the speech processor, the transistor here, the simulator, and the electrode array, which convert the pulsation received from the simulator directly to the nerve, which are related to the cochlea. And what is important here is how we the positioning of the electrode array, the implant, what we call the implant. The position of this implant is very important during the surgery. Then, because this implant has amount of 20 electrodes, and each electrode is coded with a given frequency. Then it's very important to have a good positioning of this electrode. But the main difficulties of the operation is the fact that the implant, apart from the rigid part, apart from the electrode, which is rigid, the implant is very flexible, very soft. Then during insertion, the insertion is performed manually, and during insertion, the surgeon doesn't have any perception of the cochlea. Then he just have to push it, and after check if everything is fine. Then this leads to this kind of operation where we have like the implant is get blocked inside the cochlea. We also have like this kind where we have incomplete insertion, and sometimes many times we have this kind of this complete insertion. But this kind of insertion just leads to the poor postoperative speech performance, and it's very sometimes you can cause some trauma for the patient, or lead to the membrane or something like that. Then for Oticon, they ask us to propose some simulation tools for them. First, to analyze to modelize the cochlear ramp, the basilar membrane, the cochlear fluid for the first part. Also do the same thing for the implant. Then they also need something to measure the friction force between the implant and cochlea during the insertion. The goal of this simulation tool is to use that to measure the force during the insertion, and also to see the behavior of the implant during the insertion, how the implant behave according to the direction you are given to the during the insertion. And this tool also can be used for the the planning of implant insertion. Also, they are working also for the to robotize the process. Then they want to use this simulation also for the robotized part. Then to do that in SOFA, in our team, we are using SOFA, like what Christian already presented before. Or what we are doing is lead to SOFA. We are doing it in SOFA. Then the first thing is to model the implant, and to model the implant, we use the discrete coordinate theory, which is very adapted to 1D object. I forgot to put the link of the plugin, but the plugin is open source, and you can, if you want to try it, you have it on GitHub, and it's related to SOFA also. Then to model this 1D tool, we just use this model, and the main assumption of the model is the fact that for each 1D object, we subdivide the object into finite number of sections, and the main assumption is we suppose that on each section we have like a constant strain. The strain on each section is constant, And the advantage of the model is the fact that since we are based on reduced coordinate, then the system is very small and it's very useful for the application, for real-time application. It's the kind of this kind of simulation we want to do. Then for Oticon, like I already said, they have this they have this kind of implant where we have, like here, the gray part is where we have electrode, and the blue part is the soft part with silicone. What's important also here to know is the fact that the connectors are, we don't have the same amount of connector along each section. Then each blue section has different mechanical properties. We have here is very soft, and we are coming it's more and more harder since we are going to the base. Now for us, it's very important to model all this in the simulation. For them, it's very important to be able to simulate all these things in the simulation. I will go directly to the validation part. Then for the validation, then they do in their team at Oticon, they do some tests. The first is deflection test, where they just fix the implant like that, and they apply some kind of force, and they measure according to the displacement. They measure the force required to have this kind of displacement, and they ask us to do that to compare with what they have in reality. And that's what we do in the simulation. We do that for each section of the simulation of the implant. Then for the first, when we are using the DCM, the Coursera model directly, since the Coursera model is like elastic model, linear elastic model, then we have this kind of behavior. Then we add some plasticity in the model in order to get some kind of in here. The green curve is the result from Oticon, and here we have adding the plasticities to our model. Then we have this kind of curve. We have the red thing there where we show that we can have the same behavior as what they got in the real simulation, in the real application, on the real test. The second part from them is to test what we have during the insertion. Then they have this kind of simulator. We have the same shape as cochlea. But the thing here is, as you can see, this cochlea is not deforming during the insertion. The only things which deform is the implant. Then they ask us also to do this kind of test. Here they have they put the sensor at the base of the implant, then to measure the force during the insertion of the base. For us, the main challenging part is to go from the reduced coordinate in Coursera to the global coordinate, where we are modeling the contact and the friction and so forth. Then for that, we do the same thing. This is the simulation result. I hope I can share it. Okay. I will go to my drive. I think I have the videos here. Okay. Can you just 1 minute?
We can actually see here. I mean, there is the video on Google Drive. Could you play it or okay?
Yeah, I want to play
great,
it.
Perfect. Yeah.
I have different kind of video that I only can show this.
So here it's an elastoplastic model, right?
Yeah. This is the one I can show. I want to show you also to see where we are directly showing also the contact force, because for them it's also important to know the contact force during the insertion, the contact force between the cochlea and the implant. That's the simulation we are doing for that also. And this is this one video I can play here. But this is another view of the video, right? Here I can show really the contact force what I show in the same. Then for that, for this also we show we compare the force we got from the simulation to what they have in the real application. In green here you have the result from the real application. Then for them it's very important to know from different direction of insertion. Then they do the insertion using the center line of the cochlear. They do the same thing, the center line minus 10 degrees and the center line plus 10 degrees. Then we do the same thing for this size. We have different size of cochlear. This one is the size M. Then we do the same thing for the size M. We do also the same simulation for the size S, and for the size S, we show that we are not able to complete the insertion using the actual implant they have, because this implant has 25 millimeters of length. Then we show that we can perform the complete insertion from there, and that's what they got in the real application also. Then for them, it was very interesting to see that the simulation is able to show that. And thank you for your attention. I don't know if you have, I didn't show all the results, but I think I'm over the time.
Thank you, Yinoussa. Thank you very much. I don't know if there is any question in the audience. As I said, regarding it can be a COSRA model, simulation of cochlear implant design. So, and this plasticity part that you implemented, it's included into this as a constraint in the COSRA model that you have, right?
This is we are doing two versions of this plasticity model. The second part is Camille's working on the second part. This one is directly in the COSRA part, in the COSRA simulation. Yes.
Okay. Thanks a lot. If there is no question, I mean, always the chat is yours, guys. So just feel free to post any question you like. If there is none, in the meantime, we're going to move on. But as you know, there will be time for discussions right after into the breakout room. So thank you, Yinoussa, again for the presentation. You'll be able to see more in the breakout rooms. And now it will be time for David to present the activity at PrediSurge. So it's we met several times with David in different conferences. So I'm myself eager to hear about more about PrediSurge and their work on blood flow simulation for implant design. So I think you should be able now to share your screen. Is that correct, David? Yeah, great. Perfect.
Do you hear me also?
Yeah, we hear you perfectly fine. We see your screen. I think if you go F5, it should be perfect. Yeah, there you are.
Okay. Thank you for the introduction, and thank you all for being here. So I'm David Perrin. I'm CTO of PrediSurge company, and I will be speaking about some work we do on simulation for designing and cardiovascular devices. Sorry for today, we won't speak about blood flow too much. It will be for another time. Some words about PrediSurge. So we are a software company. We are developing some solutions based on numerical simulation in the field of cardiovascular interventions. PrediSurge is born from 10 years of academic research between the Center for Biomechanics and Biomechanical Engineering in Saint-Etienne and Saint-Etienne Hospital also. So that's a close collaboration between engineers and physicians, which gave birth to PrediSurge. And what we are trying to do is to develop some solutions that we think can really help physicians in their daily activities to plan their interventions and also to perform their interventions. And we think that we can also enhance patient care and also reduce a bit the burden for the healthcare systems. All of that using numerical simulations. So our first focus at PrediSurge is endovascular repair of aortic aneurysm. Aortic aneurysm is a dilatation of the aorta, which can lead to death if the dilatation is too big. And it affects 5 to 10% of men age 65 or plus. And one common treatment nowadays is endovascular repair. And this intervention consists in deploying a stent graft within the patient's aorta. So at the really beginning, so the stent graft is inside a sheath that is inserted inside the vessel, so the aorta, and then the sheath is removed, and the stent graft, so the device, can deploy and be implanted within the aorta. And so this intervention will prevent the blood pressure to make the aneurysm grow. So it is an intervention which is quite common now, but still there are a number of complications that can happen, and especially in complex cases where the device has to be really custom made to the patient. So I can give you some examples. So for example, you can have endoleaks, which is some blood flow going in between the device and the vessel wall. So you still have some pressure inside the aneurysm, which is not good. You can also have thrombosis, so the device which can kink and block the blood flow. And also you can have some access issues where the device can do some damage to the arterial wall. So all of that can lead to some complication between the intervention or even lead to secondary interventions. And all of this is, we think, mainly due to a lack of accuracy during the planning, because physicians cannot predict each time what will happen, because each patient and each situation is different. So our idea is to use numerical simulation to predict, if possible, all these complications, and also to tune as much as possible the device to the patient. So we are working on developing a software for that purpose. We have a number of features in mind. Especially, it has to work with clinically relevant input data, and what is used by physicians are CT scan images. So we need to work with that, not to change too much the way physicians are planning interventions. It has to work for any patient and device combination. So it's really important that the solutions that we do is robust and can be used for any patient. So we use numerical simulation because what we see is that main complications are most of the time related to some biomechanical phenomena, like the interaction between the device and the vessel. So we need to represent that if we want to predict what will happen, and that's why we use numerical simulation, and especially finite element simulation. And what we want to achieve with that, so I already told you, but we want to support the choice and customization of the right device for the patient. And also, we want to try to anticipate any risk of complication. So intended users are vascular physicians and clinical specialists on the fields, who are involved in planning of intervention. So we want this software not to be used by engineers, but we really want people who are involved in the usual preoperative planning of the interventions to be able to achieve such that simulation. So the tool has also to be quite user-friendly, and to be robust, but not too complex to use. So I will present you the main steps inside our software. So first step is to get the vessels and get a mesh out of that. So we built a module where the user is able to look at the preoperative CT scan of the patient, to do like regular analysis of the CT scan, like a measurement to get the standard views he is used to. But in addition to that, the user can also generate segmentation of the vessels. So it's semi-automated. It doesn't require any kind of knowledge about segmentation, just to select the right organ on the scan. And then we also have automated vessel surface meshing that can be then validated by comparison to the CT scan. So we have an overlay of the surface on top of the CT scan to ensure that our mesh is well representing the vessel surface. Second step is dedicated to the device itself. So we have in this module the setup of the main parameters of the geometry of the device. So for example, for stent graft, usually you have a number of diameters and lengths of the body that you can input. You can also put the number of stents that you have on the device. So the stents are these black rings here that are tuned onto the graft, which is some textile. So basically, it's a small CAD interface to build the model. And once again, meshing is automated, meaning that the user just select a few geometric parameters and then everything is automated. And we also have in mind to automate all of that for standard references, meaning that in the future, for standard devices, user will just click and select the reference of the device. Once again, we have some validation with a 3D visualization of the device in the software. And then the user has also to input the deployment parameters, so where he wants to land the device inside the vessel. After that, we come to the device deployment simulation. So we have the mesh of the vessels, we have the mesh of the device, and we can run deployment simulation as you see here on the screen. So it's finite element analysis using an explicit solver. There is no needed user interaction. Everything is already set up. Material properties, boundary conditions, solver settings. So all of that is fixed and doesn't change despite having different configurations, geometries, and so on. And the methodology that we use for that is quite robust since it can, theoretically work with any vessel and any validated device, but it's really working well. We've applied this methodology to hundreds of patients and it's working really well. Finally, we go to results and analysis. So from this simulation, what you can get is a 3D visualization. In the software, you can also get an export of the device design. And since using simulation, you can customize your device. If you are not happy, you can change some parameters and run another simulation to validate that. So you can get an export of your device scheme drawing so that, for example, a physician can then give that to the medical device provider for manufacturing the device. And in addition to that, we have a collaborative web platform that can be used to share results amongst people who are involved in the planning. So, for example, you can have different physicians involved, some proctors. You can also have clinical specialists, so all of them can gather on the web platform to get an access to the 3D visualization and also to all other documents. A really important step is technology validation, because if you want a physician to use such a tool, then you need to ensure that you have really good results. So as I said before, we have 10 years academic research behind. We have a number of publication patents. We've done some validation by comparing simulation results to in vitro test, and we get really good comparison. And we also did the same by comparing simulation results to some postoperative scans also. We did a first clinical study, so a multicentric European prospective study. So 7 hospitals involved, 50 patients, where we compared some design of stent grafts that were gotten using simulation to an industrial process which involved in vitro testing. And we did some comparison, and we got a really close matching between numerical simulation and this industrial process. So we were really happy about that. But still, we know it's not enough, so we did even more. We have an ongoing second clinical study on 30 patients where numerical simulation is really used to generate custom design of stent graft. And these stent grafts are implanted in patients. And we are looking at the impact of such design process to the catheterization time in the OR and related complications. So far, we did 20 patients, and preliminary results, I cannot show them today, but it's pretty encouraging. We see a decrease in the catheterization time observed in the intervention room. And we also do some additional studies to see if we can expand the use of numerical simulation. So we are dealing with more and more complex situations, for example, involving different parts, different modules of stent graft. And also here we did 12 patients with also good results that should be published in next year, I think. So in conclusion, so we've built a software able to perform patient-specific numerical simulation to support planning of cardiovascular interventions. So it's a tool which will get into the end of physician and clinical specialist, which will allow faster planning than conventional planning today, and at least as a great design of stent graft than in conventional planning. We have some more studies ongoing to evaluate the real impact on clinical outcomes, but we really think that such tools can be really helpful and reduce the number of complications and also the time needed for the intervention. And we are thinking of some additional applications based on the same technology for endovascular repair of aortic aneurysm, because we can do much more than preoperative planning, and we also think to enlarge the application, meaning going to some other cardiovascular interventions. Thank you all for your attention.
Thank you very much, David, for the presentation. I did not see any. I asked 4 questions while you were actually presenting. I have several, but I think I'm going to join you in the breakout room for asking them. If you have, obviously, guys, additional questions, do not hesitate to ask them either to David or to Yinoussa. So Yinoussa will be in the first breakout room, and David will be in the second one. We're going to obviously have only two breakout rooms. Sorry for this session. You're gonna be free to choose one or the other, and we will maybe meet again at 4, let's say 4:30. In a bit more than 10 minutes to end the 2 last session that I will be presenting right after the pitch session and the keynote from Thierry Marchal. See you in the breakout rooms. I'll let you the floor then, Matthias. So after this industrial session, we had some time for pitching some ideas. A few of them actually came up. 4 of them, there was things about FEA post-processing for a mixed reality environment. There was other topics like neural assisted cancer treatment, combining AI and human brain intelligence. But here today, I think Matthias is available, and there was also Dr. Santosa that was around here. So I think, yeah, so Matthias has a presentation. He'll talk shortly about real-time heat transfer simulation solver. And I'll see if there is other presentation right now. Okay, so sorry.
Yeah, thank you very much.
Sorry. Yeah, Matthias?
Yep, can you hear me?
Yeah, perfectly. So
great. Okay, great. So yeah, thank you for inviting me. Yeah, my name is Matthias. Just a few short words about myself. I did my PhD at Marseille a few years ago and have since had quite a few postdocs in all kinds of applied fields, medical statistics, but also architecture. And now I'm a freelance developer focusing on web development and in particular on how to bring finite elements into not only into the cloud, but actually into the browser, onto the client. As you know, a few years ago, WebAssembly has become a platform to bring native code directly into the browser. And I think these days, this technology is vastly underused, in particular for finite elements. And these are the days to make use of it. So I've been looking at a toy project just to demonstrate the idea a little bit. There will be more colors in the next slide, and I'll show the browser shortly. But I took a toy problem, which is heat transfer. As you know, it's at the crossroads of almost any, at least elliptic partial differential equation. So heat transfer is defined by diff of cut is 0 in the steady case. And let's assume we're working on a piecewise linear complex where the coefficients kappa are the material coefficients, which designate the conductivity of the material. And there's a standard question: how can we estimate the coefficients, the material coefficients, from temperature readings? Okay, so we are given a matrix of observations where the rows are independent, and they are given just by adding a Gaussian noise onto the solution of this differential equation. And theory tells us that this is a classical low-dimensional statistical inverse problem. We have guaranteed the uniqueness and existence of solutions, and they can be found with a gradient descent method. And the prototypical application of this is quite generic. So yeah, it can be either in engineering or it can be in even in terms of curvature or domain decomposition problems, etc. But for the sake of this presentation, just think of temperature readings, okay? And the state of the art is, well, we have lots of meshes, of tetrahedral meshes for these piecewise linear complexes, say TETGAN, TET-wild, etc. They, at least TETGAN compiles very well for WebAssembly. Then we have a straightforward weak formulation of the problem, which defines the finite element formulation. I implemented the gradient computation for the log likelihood, and I'm currently putting together a web interface. A very basic old version is currently online here at this address. Let me try to also share browser, which is not as immediate as I thought. Okay, I have to stop sharing and I have to share the other window. Okay, so in particular, I've done some kind of research into user interfaces and how to visualize scalar fields. So I think that classical tactic of just slicing through the model is not appropriate for real-time applications, in particular in the medical field. So I've done quite a few user interface experiments into how to bring scalar field simulations onto the web. Right now, this is what it looks like. You can browse the temperature and query the temperature at any point. And this slice technique combines very well with current web technologies. Okay, so yeah, that's my short pitch. Let me quickly go back to the other slide so that you can see my email. And it would be cool if you, drop me a line and let me know what you think. Thank you very much.
Thank you, Matthias, for this short pitch here. It reminds me actually to a project that we have currently with so in the SOFA community, we have a project in collaboration with Polimilano, so Politecnico Milano in Italy, where the idea is to model temperature evolution due to cryoablation or laser ablation, depending on the technique, but basically thermoablation. So this could be interesting to look at also together if you're interested. There is few diffusion simulation as well in SOFA and some private codes for the GPU implementation of those models. So could be interesting to get in touch. Okay. So yeah, definitely. I think I'll get in touch later on. So not tonight, maybe not tomorrow, but when the agenda clears a little, and then I'll get back to you. Okay. So, and anyone else, if you are interested, do not hesitate to keep Matthias' email here and to get in touch. I saw Chris, if you wanna, so you wanted to talk also about maybe just like 1 or 2 minutes, if you wanted to mention your interest in CT to 3D technology that you'd like to advertise, just like a few in a few minutes. I don't know. So Chris, if we can give you here, you can, perfect. You can actually unmute, perfectly activate the cam, unmute, and that's it.
Yeah, thanks a lot for for the very short notice. I was still searching for a video, but it's very happy that you're giving me the opportunity to chat right now. Great, initiative, of course, from your end. I think it's great to have, to see all that's going on, and therefore I thought I would like to take the opportunity to share a bit what we're doing. Let me see where I can. Oh wait, I need to open the preferences to be able to share the screen, but then
there you should be able now to share it. So the slide you just saw, guys, was actually the list of people interested for pitching their work. So there was a list of 4. Chris is adding one. Just basically, if the idea here was a bit of networking. If you're interested in one of those topics, do not hesitate to get in touch. So I think I've got some for ICANN as well. I would have some contact to provide about augmented and mixed reality environment coupled with simulation. But yeah, so you should be able now to share your screen, Chris, and then after your talk, we're going to move on to the last presentation and most importantly keynote from Thierry Marchal.
Yeah, perfect. Sorry, I need to restart because of the preferences of the MacBook. So I'll be back in a second.
Yeah. All right.
Thanks.
All right, I'm going to just share the screen in the meantime. So that's for the proposal that was made. First one is the one from Matthias that we just saw, and three others. So do not hesitate to get in touch with one of those four guys attending this Inria-NAFEMS days. And right after, it's going to be the closing keynote from Thierry Marchal about the digitalization of healthcare. Okay, so Chris, are you back? I don't see Chris back for the moment, so we're just going to wait a few seconds. Hopefully he will make it. I'm sorry, I'm a bit sick. I need to just... There we go. Okay. Okay, let's wait a second for Chris. Give him, let's give him a bit the time to reconnect. If you cannot make it, otherwise we'll make it the perfect. Chris, you seem to be, yeah, you're back, right? There you are. Perfectly. We can't hear you. Sorry. You can mute it. I'm unmuting you if you can unmute yourself. Sorry.
Okay, great.
Perfect.
Thanks a lot. Yeah, so Medical VR is a startup based in Amsterdam, the Netherlands, and our core goal is to transfer CT scans into 3D models for preoperative planning. Right now, it's being implemented at the Erasmus Medical Center, the largest hospital in the Netherlands, where we combine CT scans and AI analysis to be able to preoperative plan complex lung surgery. So just basically to give a 3D representation of the patient's anatomy. So the basics, of course, is a CT scan, but it's more important to give you a bit of an idea of how, sorry for this.
Maybe you can cut the sound, because I mean it's hard to hear here.
Yeah.
Yeah, perfect. Thanks.
No. Sorry. So it's most important that this is exactly what they're seeing. So in VR, they get a proper idea of how the tumor is located and where it's located compared to the current procedure. So this is the location of the tumor, and also it shows the other anatomic views. The whole reason why I actually asked, of course, to be able to give this goal is that we're combining basically video, turn it on, stop sharing. Yeah, sorry. So the main reason why I'm asking for the stage here is that we're searching for other parties, in France, or wherever in Europe, to be able to see how we can combine, if you have the specialties within DICOM, if you have other algorithms which could be very useful, which work with DICOM formats or other types of information, medical information, how that can be combined for preoperative planning or for training. We see that the technology for virtual reality combined with AI really steepens the learning curve for resident students, because it's a safe environment where they can practice, they can get a good idea of how the anatomy of a patient is built up. So it's a whole new setup of learning next to the operating room or the classical way of books or videos and such. Yeah, so this is just a very short lesson.
Oh, perfect. I think that's I would say the philosophy was to drop an idea and to seek for partners. For image processing, we saw MedInria before. That could be interesting to include in your own solution segmentation algorithms coming directly from research teams. In MedInria, that could be included into your product. Yeah. And for VR, I would say VR plus simulation. I already mentioned that earlier and in previous messages here. But we have a company working on this very specific topic, coupling simulation with VR, called Infinitech 3D. So that do not hesitate to contact both of them.
Yeah. Yeah.
Thanks.
Yeah, that sounds very interesting indeed. So thanks a lot for that. And but yeah, we do have a new demo in Paris in a couple of months. So maybe it would be nice if we could.
Yeah, definitely catch up there. And yeah, I'll stay tuned. Maybe I'm going to follow your activity on social media to make sure to get it on time.
Great, thanks a lot.
Yeah, thanks a lot, Chris.
Thank you very much.
Let's move on to the last session here. So keynote session. I'm just going to take the proper slide here. And there you are. Keynote session from Thierry Marchal, who is working at ANSYS, and here representing the Avicenna Alliance. It's actually the first time we were also in this context of this Inria-NAFEMS connecting together, Thierry. It's a pleasure to welcome you and to have your keynote about digitalization of healthcare. The floor is yours. You should be able to share your screen. I'm going to make sure of that. Thierry, there you are. Okay, perfect.
I think you should be able to see it, right?
Perfectly. Thanks, Thierry. The floor is yours.
Okay, well, thank you very much for this invitation and for the introduction. Good afternoon to all of you. Good morning, because I've seen that we've got several people from the US, and good evening for people in Asia as well. Sorry for this long title, and well, it's very difficult to wrap up such a very nice conference here where we were learning a lot of things. Yet, I would like to say that we don't do enough, or more exactly, we need to exploit more the research that we are doing here, because when you look at that, the kind of activity here, the increase of the cost of healthcare, this is unsustainable. And look at the bottom, more than $2 billion to get a new drug or a new vaccine to the market, and taking more than 10 years. Can you imagine 10 years to get a COVID vaccine? That's something impossible to do. And for that, I think that this kind of dramatic pandemics have been extremely useful, because it was illustrating that this kind of in silico approach can be a key component in order to accelerate the process here. This is not something that's completely new, because we knew already about that, and leading companies like Medtronic and others were thinking that the in silico method was essential. We had to move away from this kind of one-size-fits-all to go to personalized situation. We need to complement in vivo and in vitro approach by this kind of in silico perspective. But some of you may argue that, in fact, although the healthcare industry is investing a lot in R&D, that clearly are laggard in terms of simulation. Things is changing because of all what I was telling you. And it's quite clear that the healthcare company, the healthcare industry will be catching up on that. And that's starting this year. We can see that the investment in simulation in silico method is increasing at a CAGR year on year of 25 to 30%. So definitely, you are in the right place to invest over there. What are we doing? What are they doing with all this kind of in silico approach? We've seen that through the day-to-day. People are developing this kind of virtual human laboratory. We've seen this model of liver, brain, heart, and so on, so that we can aid the environment and predict how a kind of new device, a new drug will behave in this kind of environment. People are pushing it further to do this kind of in silico testing and all the best practice that we can see in the industry and the academic world as well. The fact that Hugo, myself, all the previous speakers, we are different. And therefore, it's important to make sure that we can make sure that the device will be working everywhere. But this is not enough. And at ANSYS, where I'm working, one of my responsibilities is that we are trying to build this kind of healthcare program, which is different initiative, different level. Building a network, academic and clinical network, making sure that we've got this kind of digital transformation that I will review. Creating this kind of virtual organ, and some of them have been presented today, heart, brain, lungs, and so on. Not just for the sake of developing this kind of digital twin of the heart, but to create a platform where we can test new devices, test new innovation, and innovate faster. And therefore do this kind of in silico clinical trial that some were mentioning, pushing it further, like David was mentioning, with this kind of clinical apps. And the ultimate grail, what we should be achieving, is this kind of personal digital avatar, a digital twin of yourself, able to predict what will happen in your body and prevent the disease. that is kind of holy grail that we can pursue all together and we can achieve. And of course, all that is driven by this kind of AI and digital twin over there. Well, let me come back to some of these elements. First, in terms of digitalization of healthcare, and the previous presentation, Chris was showing that this is not just about creating a model, even a very complex model, in this case of a skeleton, where you need the boundary condition, you need the geometry, and you need the material properties. This is also involving this kind of post-processing with VR. This is also involving making sure that we are doing several situations, design of experiment, in such a way that we can manufacture that. It could involve additive manufacturing, simulation process data management, because we need to make sure that we are digitalizing the entire process. And when we are talking about this kind of virtual organ, let me make reference here to a fantastic presentation that we've got from Professor Merrin Taifei from the University of Auckland, where over there they're developing and validating a model of the cardiovascular system together with the pulmonary system, in order to make sure that future COVID situation, we can model that. We can model this kind of solution. We've got the right model created before. That's the role of creating this kind of virtual model. But I was telling you that we cannot afford to reinvent the wheel. So that's why a few years ago, we were joining forth as part of the Avicenna Alliance, this kind of global organization. Global because it involves academics and industry. Global because it covers people from North America, from Europe, from Asia. Global because it involves pharma, software, medical device, and even cosmetic people, but also small and large companies. With the mission which is quite ambitious, to say that we want to accelerate medical innovation in order to make sure that we have a safer, more affordable healthcare, exactly the point that I was stressing at the beginning, and also cost efficient for us. The particularity of the Avicenna Alliance is that the method that we are using is only in situ method to complement what others are doing. We believe that this will be a key element for the future. We are joining forth, and you can see several of our members. And by the way, I would like to mention people like Mathieu, Mark, Simon, Christophe, who are part of the team today, who are very helpful to do that. But we are not just working with all this academic behind the VPH Institute and all this industry here. It's very important that we are driven by the key people, like the regulator. So working and partnering with the FDA, the EMA, the European Commission, but also working with the standard organization. Because as I said at the beginning, we don't just want to do some research. We want to make sure that this research can be directly applied and to accelerate this process. So what are we doing from there? This is leading to a new best practice. Beyond this kind of innovation is simulation-assisted FDA approval process. All the models that you are developing, push them further than just research. Make sure that this can be used in order to accelerate the long and costly regulatory approval process. And by the way, this is a slide coming from the FDA itself, saying that indeed, this kind of digital evidence is a reality, provided that this is properly validated. We will accept that. And some of you might be saying that, oh, you know, digital twin, that's a fantasy for the future, and we don't know about that. Not at all. The FDA itself, once again, is saying that indeed, using virtual patient for regulatory approval process is a situation today. Digital twin is the future, is a near-term future, and we've seen today that this future is already happening as we speak. So that means that we can use all these computer models, all the advanced research that you're doing, and exploit them for regulatory approval process. Well, there's some way to do it. And one of the easiest ways is that to say, well, on the left-hand side, this is a traditional method. For every single model, you need to do, for example, this very complex fatigue and time-consuming fatigue testing model. Well, if you can identify what is the worst-case scenario through simulation, you just need to validate this kind of worst-case scenario. If it is okay, that's okay for the rest of the element. That's just for a kind of simplified situation. What about the others? That's one of the key elements. It's great to say that we can use digital evidence for regulatory approval. The key question that every single company or researcher will have is, how can I do that? What is the process? Tell me how to do that. And you can see on the left-hand side that there is a document from the FDA and now also from European authority saying that indeed computational modeling and simulation can be used for regulatory approval. How to do it? You can see the second one, which is this kind of VNV 40 document published by ASME about medical device extended to a pharma company. And if you want to validate fluid, electromagnetic, structural modeling, there is VNV 10, VNV 20. And then the last step is that when you are post-processing the result, you can do it under the guidance of the FDA. Europe is lagging a little bit behind for that. And let me call on all these European people in this call here in order to make sure that we are pushing the ball and we are making sure that we are catching up on US people and making sure that we are doing that in the rest of Europe. But more specifically, what do we need to do? We can validate a model. We need to define what is the question of interest. And for that, let's try to define what is the context of use of the computer model that we will get here. Let's try to assess the risk. Is the computer model very impactful on this element? Is this kind of solution threatening the life of the patient? Based on that, the validation that we will be requesting will be defined. When we have this kind of risk assessment, we can go to the credibility goal. What do we need to do in order to do this kind of risk assessment? Establish the plan of simulation, execute the plan, and reach the final conclusion. If it is positive, we can post this result. Of course, this is summarized in one slide, this kind of 70-page document here, which is going into detail, and that ASME is giving some training. I like to stress that, well, this is in North America, but there is a very nice white paper published by Marcus Reiterer from Medtronic, Mark Horner from Ansys, and Cécile Rousseau from Voisin Consulting, making a comparison to see how we can do that across the world. And you can have a comparison here of the different process. With one goal that we should all have is how can we make sure that this kind of in silico clinical trial is becoming a routine. Within a few years from now, how can we accelerate this kind of regulatory approval process? We've got all the components. We've got access to computational model, especially through cloud. We've seen several times today that we can have access to a large number of patient-specific geometry. The library of material properties. We've seen some model of different kind of disease. We are creating this kind of standard. We have all the bricks. Let's put them together under this kind of environment, just like Maxime was showing it sometime. And this is for real. Look at this slide presented by Michael Hill from Medtronic in front of the European Parliament as part of an Avicenna event. By using this kind of computer model of the pacemaker and the heart, this was reviewed and approved by the FDA. This was saving them 2 years of work, saving them $10 million. But the most important, in these 2 years, they were able to treat 10,000 patients who received this new technology. That's one of the elements how we can exploit all the nice model and research that you're doing. I'd like to stress another one, which is maybe more futuristic, but nevertheless a nice reality. And because this is not NAFEMS France, let me take an example from the hospital of Poitiers here, presented by Kevin Aubert. You can find the full presentation online. These people are working on some kind of very complex situation where there are some people having some kind of advanced fracture, very complex fracture of the tibial plateau. And in France, in Poitiers, just be proud of that, they developed this kind of new technology, tuberoplasty, where in order to put all the different components in the right place, rather than making a big opening, they're inserting a small balloon in order to guide all the components, and then they will be stabilized. The drawback is that for the surgeon, very difficult. A small scar over there, great, but they cannot touch the segment. They cannot see all this kind of component. So that means that they need to do a lot of preliminary work. In addition to that, people are different. They could have different kind of osteoporosis, different kind of geometry. So what are they doing? In terms of pre-operative, that's what I was mentioning to you. They create this kind of model in order to understand all the different components will be moving under the balloon. And then they need to create this kind of patient-specific model for the stabilization. One of the key elements, which is always true for in silico, validation. Validate, validate, validate. Validate, compare with what's going on in the reality. This is one of the key things. Let me first focus on this first element. So they were working on this kind of comparison, a digital twin, a computer a model of the tibial plateau, where they were introducing this kind of balloon and the reality, and seeing that they've got some very nice comparison. Of course, they were doing some kind of parametric analysis. What is the position of the balloon? What will be the result happening here? The second step is this kind of stabilization of the process. And for that, once again, you've got several parameters. The screw, the length of the screw, the position of the screw. Do you want to add some cement or not, depending upon the position of the patient? So this technology can be used for pre-surgery planning despite the complexity of this element, and therefore help the different patient. That's one illustration, but there are so many others here that we can see, and we've seen other, like from Perrin today from PrediSurge and so on. So definitely an area where we want to go. And to wrap up, what I want to say is that this kind of in silico medicine is a proven technology. That's a reality. And by the way, we have no choice. We have no time. We need to move into this direction. But what is extremely important, we don't have time to compete. We need to work together. That's part of the Avicenna Alliance, where we've got some kind of a pre-competitive collaboration. We've got the technology. It is not perfect, but it already can save quite a lot of life and improve the comfort of patients. Regulatory people are open to talk with us. Let's take advantage of that. Clinicians are willing to go there. So what is missing for me is this kind of focus and priority. Let's make sure that we are going there full speed, and to make sure that we are going. And because time is there, I want to thank you very much for your time. There are so many things that we can say, but not enough time here. And certainly, let's be connected on social media. Happy to answer any of your questions. And thanks again for your time and for the invitation.
Thank you very much, Thierry. Very nice and dynamic presentation. Really, I liked it very much. Is there any question in the audience already? I did not ask directly in the chat, but as usual, if you want to either post it in the chat or unmute yourself and ask your question directly to Thierry. And I'd like to start actually with a very basic one, which is regarding the Avicenna Alliance. You know, I'll really talk for my own house, like for research. When should we, or when, where, for which reason should we, get in touch with Avicenna Alliance as soon as we want to get included into this whole pipeline that you presented, or as soon as, like, should it be research teams, or rather when there is an idea, a startup working on a specific topic, should they contact you? Just to know when and who should contact the Avicenna Alliance.
Well, you can always contact me to join the Avicenna Alliance, and by the way, we have a special rate for a startup, €1,000 per year, and you can have all the access to the people. We've got three major working groups. One is international, working with all the group, all the agencies around the world. One is regulatory, in order to make sure what can we do. But one is a research and technology group led by Liz Garris, who's the director of the VPHI. By joining this kind of research and technology group, that means that you are collaborating with all the members that I was presenting, with all these academic people, and therefore the work that you are doing is not done in silo anymore. It's part of this kind of global ecosystem and become a kind of a key component. On top of that, that means that the people can see the value of it and make sure to engage with the FDA, with all the people, in order to see how we can deploy that further. By the way, we are very happy to engage yourself with the FDA, speaking in front of the European Parliament and all these kind of things. So be ready to do that. But for research, yes, you need to join, definitely. Okay.
And yeah, I definitely see the connection also with what as you said, what David earlier from PrediSurge presented. It makes really the connection, and it made me also. That's the second point I wrote. It was I'm always pushing research teams for going more for open science, like publishing the papers, publishing the results, providing availability for others to test what has been just published. I think it's something which is always helping making things, as you said, faster for fostering new things. I mean, fostering new technologies from research to to really to the clinical application.
Yeah, you're perfectly right for that. I was chatting with Maxime Sermesant, who was making a very nice presentation earlier, and I like very much what he was mentioning in the chat. To say, okay, we don't have time for competition. We don't have time to reinvent the wheel. So that's why we need to publish. And of course, there is some competition between academic and between industry. But we can have this kind of pre-competitive collaboration and make sure that indeed we are changing healthcare. After that, we can think about competition. But there is so much to do. Well, there's a lot of room.
Thank you. You've got a question from Agus Hadi. Dr. Marchal, could you explain the state of the art of the use of the numerical methods you design minimal invasive medical devices? So I guess, yeah, the state of the art of the medical device you presented. If you want, yeah, go ahead.
I guess that this is related to this kind of clinical application which have been made. So what is very interesting is that this clinician, we are taking this kind of commercially available general purpose tool and just customize the tool in such a way that they can apply it for this specific application, which is great because this is just a standard one. One of the challenges over there is to compare that with anything which is clinically present and therefore to validate the process. When you can go through this element, well, this could be deployed in any kind of hospital around the world. So this is perfectly available. The challenge that we are still facing right now and that prevent this kind of pervasive deployment of simulation in clinical application is this kind of expertise which is still needed. So that's why when I see the work of David Perrin and others who's trying to embed all that behind an interface, this is great things. The second and probably the biggest challenge that we are facing is acceptability. People are reluctant. They don't know why, but they don't trust that. And well, if I may say, that's a little bit like people who doesn't like a vaccine for COVID. Why? Well, I'm not sure for that. Well, here, let's try to see what could be there. We need to convince people. That means that we need to listen to the question and answer them. We need to validate more. But there are many people who are doing that, mentioning Boston Children's Hospital. Some doctors are using that in order to save the life of children with major heart malfunction. So we can fully trust this kind of approach.
Thanks a lot. Is there any other question? Thanks also, Agus, for the question. If there is any other, do not hesitate to drop the question in the chat. In the meantime, I'm going to prepare the sharing, because it would be then the conclusion. I mean, it's not that late, but it's quite always a bit long when we are fully online as we are today. I hope. By the way, Thierry, we will meet for other occasions. Thanks again to all the speakers for taking the time to prepare the presentation. Thanks to the audience for participating. As suggested by, it was Marcio who wrote to us privately. I think it was a good idea. We're going to share, using the list of emails that it was only used to this purpose, actually, to contact you before and right after this session to make sure that you get access to the recording. And secondly, as well, to have access to all emails of the presenters so that you can actually have contact, keep the contact if you missed it, or for people that would have looked at the video afterwards, so to make sure that maybe they were in South Korea or in the US, as Thierry said, there was people connected from around the world. So to make sure everybody get all the information, we'll have a summary email giving the video link and all the contacts for the speakers. Thank you again for attending this Inria-NAFEMS Day. Thanks to NAFEM for organizing it together. It was a pleasure, and hopefully let's make another session about other Inria technology later on, or just updates about those technologies you've seen today. Thanks a lot, and do not hesitate to provide us feedback about this afternoon. If you are curious, or if you need any other information, just send us an email. We'll be pleased to answer you. Thanks a lot. Have a good day, and bye. I'm going to stop the recording.